the following section is on finding the nth root of a number. This is section 1.6, chapter 1, example 15. We'll go through this example first and then outline the general points. So we are asked to solve the following equation. Z cubed is equal to 1. If it's z to the power of 3 equals to 1, we are going to find 3 solutions. You may remember having questions of that type last year. You did those questions by factorizing, so rearranging first of all, and writing z cubed minus 1 equals 0, factorizing it, and then finding the real solution, which would be z equals 1, and there will be 2 other solutions which will be complex conjugate pair. We're going to learn a slightly different, well, a very much different method from the one before, and the one that would work if you were to solve z to any power equals to 1, or indeed another complex number. So the first thing you need to do is you need to express 1 in terms of either modulus argument form or exponential form. So we are going to need to find what modulus of that number is, which is simply 1, and what the argument of that number is. So the argument, well, this complex number is simply 1 on the real axis. The angle is 0 radians or 0 degrees, but we're going to use radians. Now, here is what you need to do. You need to actually write the general form of this argument. So any argument that is repeated 360 degrees, every 360 degrees, will take you back to 1. So you could actually say argument 0. If you say argument 2 pi, which is equivalent to 360, would also take you to that point. If you add another 360 or another 2 pi to take you to 720 degrees or 4 pi, this will be also, if you were to write it in Cartesian form, it will take you to the complex number 1. So to take account of that situation, we're just going to add multiples of 2 pi. So you write 2k pi, add it to our argument. So it's actually 2k pi. And any complex number that you start off on the real positive imaginary positive real axis will actually have 2k pi as its argument. So we're going to I'm going to use exponential form because it's a little bit more efficient. So it's 1 e to the power of 2k pi I is what my 1 equivalent to 1. So we need to find the cube root of that number. So we're going to cube root it, i.e. raise it to the power of the third. So you get z is equal to e to the power of 2k pi I raised to the power of the third. So multiply the powers, so it's 2k pi I over 3. So this is a general root, but we need to find 3 different roots. Okay, so the first one you take the consecutive values of k. So you normally will take a value, maybe start from -1 or -2 and then go to 0, 1. You could actually pick 0, 1, 2 and then adjust the argument so it falls between minus pi and pi. So it doesn't really matter as long as these values here are consecutive. So I'm going to, for this example, start with -1. So it's going to be -1 substituted into this argument. That will take you to -2 pi thirds times I. So minus 2 pi of, yeah, it's within between minus pi and pi, so that's okay. Then you put 0. If you substitute 0, that will take you e to the power of 0, that's going to be 1. And then when you put k equals to 1, you're going to have 2 pi over 3. So z is equal to e to the power of 2 pi over 3. Since the question does not specify which form to give the answer, let's write all three forms out. So here we're going to substitute it into the modulus argument form. So it's minus 2 pi thirds add I sine minus 2 pi thirds. If I ask you for this form, you leave it like this. Don't take the minus in front of the I sine bit. Just leave it like this. Let's just work it out. So cos minus 2 pi over 3 is going to be minus a half. And then sine is also going to be, no, actually, sine is going to be, for minus, it is also negative minus root 3 over 2i. We are actually in the third quadrant, both sine and cos are negative. This one, you put cos, the argument is 0, plus I sine 0. If you are asked to write it in this form, that's how you've got to give the answer, and that's just 1. Okay, and then over here we've got, oh, by the way, if you wanted to just the exponential form, that the same thing follows. You have to write it like this first. Okay, forgot an I here. So this one is cos 2 pi over 3 plus I sine 2 pi over 3. So this time we are going to turn to the second quadrant. Cos 2 pi over 3 is minus a half, and sine remains positive, root 3 over 2i. Obviously put those into the calculator and work them out. Don't risk making a mistake. So this is part A of our example. Now part B, it says to represent your solutions in part A on an Argand diagram. So let's just do an Argand diagram over here. You do not need to be really accurate with where you plot the points. Luckily I've worked it out, so pop it's, you know, minus root 3 over 2 is going to be bigger than minus a half, but really it doesn't matter. So if I said minus a half is here, and then minus, let's say somewhere here, it doesn't have to be exact. So that's my first complex number. I choose to represent it as a vector. I'll label it with exponential equivalent. Okay, the second one, or the last one, I'll pop it over here. So this one here will take you to plus root 3 over 2i. Either plot it on there or write it here as a 2 pi over 3i, or plot it over here. It's up to you. Actually, what we're going to label is 1, 2, 3. Let's call this one 1. That was 3. And then finally, this one needs to be the same length. We're going to imagine this is length 1, so it's going to take you somewhere here. That's 1. And that's going to be z2 is equal to 1. Let's do it. Right. So finally, it says, show that the 3 cube roots of 1 can be written as 1. So this is part C. This was part B. 1 omega and omega squared. In fact, the roots of 1, they're called the roots of unity. They do like this notation of omega for one of those roots, and then omega squared will be the other root we will see in a second. So let's check the fact. So if we say 1, we already have 1. If we say omega is going to be minus a half minus root 3 over 2, or if you pick omega is equal to minus a half plus root 3 over 2, it doesn't really matter. So it should work out in both ways. I'm going to pick my omega as my first root because that's the one that I've written as my z1. So if omega is minus a half minus root 3 over 2i, so if I write it in its exponential form, and we've been asked to then find omega squared. So I'm going to use the exponential form, and then using de Moivre's theorem, I'll get e to the power minus 4 pi over 3i. Now, if you notice 4 over 3 minus 4/3 is less than minus pi, so we need to adjust the argument. So minus 4 pi over 3, let's add 2 pi, so it falls between minus pi and pi. So this is going to be 6 pi over 3, add to minus 4 pi over 3 leaves you with 2 pi over 3. So it's e to the power of 2 pi over 3i, which is identical to our last complex number over here. So this one would be your z1, and then this one has got to be z3. And then we've got to check that the following is true. 1 plus omega squared is equal to 0. We've got to show this. So we're just going to substitute our complex numbers. So it's going to be 1. Let's use the minus a half minus root 3 over 2i for our omega. Now omega squared is e to the power of 2 pi over 3i. This is our last complex number, which you could see that's minus a half at root 3 over 2i. So if I add this complex number, what am I going to get? Well, the imaginary parts, you've got minus here and then plus, that cancels, and then you are left with 1 minus a half, which is clearly 0. So it's been shown. Okay, so let's just go over general points, things that transpire from this method. So if you are asked to find a root, nth root of a complex number, here we've done the root of unity. The first thing you do, you've got to, so you've got z to the power of n is equal, let's say, to a, where z and let's say a plus ib. Okay. Are complex numbers. The first thing you do, you're going to find modulus and argument. Let's call it r and theta. So I'm going to rewrite my a plus ib as r e to the power of I theta. So whether they ask me for trigonometric form as the final answer or not, this is nice to actually work with this notation and then change it to the one that's required. Then you're going to use de Moivre's theorem, but before you do that, you're going to account for the fact that this argument repeats itself every time you do a 2 pi turn. So you put 2k pi is the argument. So over here we are going to add 2k pi, and in here. So as soon as you found the argument, add multiples of 2 pi to the argument. Then we are going to raise it to the power of 1 over n, because that is finding the nth root. If I raise z to the power of n to 1 over n, you are left with z. And here you do r e to the power of I theta plus 2k pi raised to the power of 1 over n. So this was just a thought here. So then you are going to tidy this up first. So you're going to raise r to the power of 1 over n, and then you're just going to tidy this argument. I'll put 1 over n at the end, but you could write it in front. And then use n lots of consecutive values of k. So if n was, for example, 5, you may choose -2, -1, 0, 1, and 2 as your values, and then check the final arguments are within -pi and pi. If n is equal to 4, you might need to choose -1, 0, 1, 2, as long as the values are consecutive. You may always choose 0, 1, 2, etc., and then adjust the ones that fall outside the required range. Okay, so the next stage is we're going to move on to example 16. Before we move on to this example, we're just going to have a quick look at roots of unity. So I have mentioned the general way of solving an equation, but this is just the properties of roots of unity. So in the previous example, you actually have met one of those properties. So if you are solving z to the power of n equals 1, the solutions is always the following. So this is the general solution. Z is equal to e to the power of 2k pi over n, or 2 pi k over n I. I think the book used 2 pi k over n. Doesn't really matter as long as it's multiplied by k. And then, depending on the value of n, this is how many different values of k you will pick. And then this way you'll be able to identify n distinct solutions of that equation. So they're looking for n of them. Now, given the nth root of unity is e to the power of 2k. Oh, no, we don't want which. Okay. Yes, I was just thinking why we did that. Yes, one of them. So let's say you chose k equals to 1, and you pick one of the roots as 2 pi over n I. Okay, so here we set k equals 1. Then the other roots are simply 1. Well, we already have omega squared, omega cubed, all the way up to omega n minus 1. So those roots, you don't need to be substituting k equals 1, 2, 3, or, you know, till you get to n minus 1 lots of, to n lots of them, the solutions. You may actually choose to, once you've identified the first root, multiply that root by itself to get to the second root, then multiply that answer by the original root to get to the third one, etc., etc. So that's a nice way of doing it. Or simply just squaring this one. So it will be, if you started with 2 pi over n I, you square it directly, you will have e to the power 4 pi over n I. If you raised it to the power 3, that would be 6 pi over n I, etc., etc. Now, if you were to plot all the solutions to the equation z to the power of n equals 1 on an Argand diagram, you would draw a regular polygon. Regular polygon, it's called n-gon in the book, but it's a regular polygon with n vertices. And not only that, when you add all the roots, they will always add up to 0. And you can see here visually, if this is 1, this is actually, you've got octagon here. So it's z to the power of 8 equals to 1. You could see how it's nicely in equilibrium. -1 is balanced by 1. minus I is balanced by I. Over here, you are going to have, I think this one is going to be 1 over root 2 plus 1 over root 2 I. Well, this one will have imaginary part that's in opposite side. So the imaginary, if you were to add these two, you will cancel the imaginary part. But then if you add these two, the real parts cancel. This whole diagram is in equilibrium. Now, one thing I haven't noticed here, written here, it's centered at the origin. So that's a very, very important fact you need to memorize. Okay, so now we're going to have an example of how to find the roots of a different complex number to 1, so not roots of unity. So let's have a little look at this problem. So I've already gone through the steps. The first step we're going to do, we are going to find the argument and modulus of this complex number. So let's do the modulus. So the modulus is 2 squared at 2 root 3 squared, square rooted. So this is 4 at 12, 16 square rooted. That gives me 4. Argument is going to be, well, I like to draw my Argand diagram, a point on an Argand diagram, so it's 2 across. So that's going to be 2. This is 2 root 3. We are looking for this argument over here. So this is clearly either arctan or tan inverse of 2 root 3 over 2, which is root 3, which gives me 60-degree angle pi over 3. As soon as you've written this, you've got to account for the fact that you will have infinite number of these values for the arguments, which are 2k pi lots apart, or 2 pi k. Right, so this is going to be my argument of my complex number 2 plus 2i root 3. So let's write down the form, exponential form, 4e to the power of pi over 3 add 2k pi I, and then undo that, raising to the power of 4, so giving it the power of a quarter. So surround it with brackets first, or you may do it quicker, but let's do it slowly to begin with. Okay, so here we're going to raise 4 to the power of a quarter. Now, if you pop this into the calculator, it'll give you a decimal as the modulus of that number, and you will lose marks. So very carefully, just think, if you're finding a 4th root, it's the same as finding a square root, so raising it to the power of a half, and then a square root of that answer. So 2 square rooted is root 2. Okay, so root 2 e to the power of, I'll times it by a quarter, I'll put a quarter at the start, it's 2k pi over I. Right, so all we need to do now is find 4 solutions, since it's to the power of 4. So let's pick, I don't know, let's start with minus 2, and then go to minus 1, and then 0, and then 1. So the first complex number is going to be root 2 e to the power of a quarter pi over 3. Let's add minus 4 pi to this I. So 1/3 minus 4 times 3 is minus 12. So it's minus 11 pi over, let's just do it on the side. Obviously you can do it with a calculator, probably better. Okay, so this is going to be minus 11 pi over 12. Good. Okay, so it's root 3 e to the power of minus 11 pi over 12. You may choose to write it in modulus argument form, but I haven't got much room here, so I'll leave it. This is perfectly within our range. Minus pi is bigger than in size than this value, so it stays nicely in the required interval. Let's do the next one. Put -1 into this, so it's e to the power of, if I put -1 here, I'll have pi over 3 minus 2 pi, and this is going to be 1/3 minus 6, so -5 thirds, but times by a quarter, so minus pi, 5 pi over 12. I'll get straight away. Why did I put root 3 here? Minus 5 pi over 12 I. Okay, see those two numbers are minus 6 over 12, which is a half of pi apart, which I would expect because it's 2 pi rotation. You are sharing it between 4 numbers. You might think about this regular polygon. So they are pi over 2 apart. So let's do for the third one, root 2. This is going to be e to the power of, that goes to 0. You are left with pi over 12i. Again, I could have just added, let's see if I added, this one, add, if we go this way, 6 pi over 12, rather than working it out from the original equation, I could just do the jump, add half pi to that. Okay, so last one is going to be root 2 e to the power of, again, if I add 6 pi over 12, I will get to 7 pi over 12. I'll write it like this, but let me just check. If I put 1 over here, I will have a quarter, and then pi over, somebody is the assistant. I'm sorry, I have to wait till I finish this video. Okay, so 6 pi over 3 added to that is 7 pi over 3, 7 pi over 12. Great, so we've done example 16. We'll move on to example 17.